Okay, when it comes to 7.7, we're going to talk about the graphs of tangent, cotangent, cosecant, and secant. We're not going to go quite as deep into these. We need to understand them. We need to definitely understand the domain and range and the general graph. We're not going to go quite as deep though, okay? And before we dive into the graph of tangent, our first one, I need to remind you to make sure you understand the difference in the unit circle compared to just the XY plane. While the unit circle lives in the XY plane, the unit circle is a tool that we use to understand angles in radians or degrees and the corresponding ratios of those trig functions that we end up getting as our output values. You need to understand that when we graph these trig functions, they're living in the standard XY plane. Okay, so we're going to have our regular old x-axis, our regular old y-axis. It's just that now our x-axis is going to be broken down into radians because the input of trig functions is still some angle. And then the y-axis is going to represent those ratios, okay? So the graphs of these trig functions, while they are deeply related to the unit circle, just understand that the x's and y's on the unit circle represent something kind of different than the x's and y's when we graph the functions, okay? So let's talk about tangent. Now, really quickly, I want to remind you that tangent is the ratio of sine over cosine. And that's really important for a couple of reasons because when we go to the unit circle, we need to understand that tangent's the ratio of those points on the unit circle, sine divided by cosine. And we also need to understand that when you're dealing with tangent, cosine can't equal zero because if cosine is zero, this whole thing is undefined, okay? And what we find is that we're going to have these things called vertical asymptotes when cosine is zero. So if you're like, what in the world is a vertical asymptote? Please stop this video now and go into the Math 171 content and review vertical asymptotes because you most certainly talked about them, I believe, in chapter 5. Okay, so let's get to tangent. Tangent is going to be our first graph. So we're dealing with y equals tangent of x. Okay, so you're not seeing tangent of theta because we're graphing this in the xy plane. Just know that x represents an angle. So when we draw these graphs, you're going to see that the x-axis is broken up into radians, and then the y values are going to be the ratios that tangent spits out. Okay? You could also see this instead of y equals tan x, you could potentially see f of x equals tangent of x. Okay? Now, we found out earlier that all trig functions are what we call periodic. That just means that in some very specific pattern, the trigonometric functions repeat. And what we found was they repeat for sine, cosine, secant, and cosecant, they repeat every 2 pi radians. Well, for tangent and cotangent, they repeat more frequently. They repeat every pi radians. So the period for tangent is going to be pi radians, okay? Now, when it comes to the domain, back in 7.5, this is that time where I was like, man, I hate telling you that sometimes you just have to trust me and it'll make more sense later. We're at that later point. We're finally looking at the graphs of sine and cosine. So now hopefully the domain and range is going to make more sense when you get this visual of what these graphs are. But back in 7.5, we were looking at the domain of tangent and we realized that we have issues at every odd integer multiple of pi over 2 because at odd integer multiples of pi over 2, we have cosine equaling 0. Okay, so that's kind of a problem. We can't have a ratio with 0 in the denominator. And so we made this separate video all about how we could write out the domain of tangent kind of more formally. Because if we say, hey, the domain of tangent can be like anything except odd multiple integers of pi over 2. Like that's well and good. That's very conversational, but that's not very formal. So we had to come up with a formal way to write the domain of tangent. So we were acknowledging that we have some input value. Now that we're back to the regular old Cartesian plane, we can say we're looking for values of x such that. And then instead of listing everything that x can be, we need to list everything that x cannot be, okay? So we want to start by saying x cannot be the following, okay? Well, what happens with this is x cannot be pi over 2. If we're going around the unit circle, we see that the first time cosine is 0 is at pi over 2. The next time cosine is 0 is at 3 pi over 2. And then if we go another pi radians, we get 5 pi over 2. And then another pi radians, we get 7 pi over 2. So odd integer multiples of pi over 2 are a problem. So we start with pi over 2, and then we realize that, hey, if we take pi over 2 and we add pi radians, we get right back to where we start from in essence. So we get the next iteration and we add pi again, we get the next iteration. So we had pi over 2 plus pi is 3 pi over 2. Add pi again, we get 5 pi over 2. Add pi again, and we get 7 pi over 2. So we realized if we add k multiples of pi, we're always going to end up at a situation where cosine equals 0. So pi over 2 plus k pi, but that wasn't enough. We had to tell our reader what in the world is k. Well, k is an element, so we use that weird like curvy capital E of the integer. So that weird Z with the double bar, that's the symbol for integer. So that's our formal way of writing the domain. Okay, and remember the domain restrictions occur when cosine is equal to 0. And what happens is we end up with vertical asymptotes when cosine is 0, and cosine is 0 at its x-intercepts. So we get vertical asymptotes at x-intercepts of cosine. Okay? So that's some basic information. Now, unfortunately, I think this is one of those tables that won't let me write in it. I don't know why some of them let me and some of them don't. I don't know what I've done with my setup here, but something's off. So what we're going to do is you all have this worksheet sitting in front of you. So let me kind of describe the table. We're going to do just like we did with sine and cosine, where we fill in a table of values. Okay, and then we're going to use that table of values to plot these points so that we can get the graph of tangent. Okay, so the first column of this table represents measures for angles, so theta, so values for theta, positive and negative here. So what you're going to notice is we do start the tangent graph at negative pi over 2, and then we go to pi over 2. So notice from here to here is pi radians. So that's one whole period of pi. We just start at negative pi over 2 and go to pi over 2. Okay, so we're going to note that the first column is measures of angles. The middle column is where we evaluate and find the output. Okay, so we find our ratios. And then the last column is going to be the ordered pair on the graph. Okay, so I'm going to go to a separate document so we're not dealing with the bounce. Okay, so let's scoot over to here. Okay, so you've got your table in front of you, follow along. So we're starting with pi over, tangent of negative pi over 2, okay? So tangent of negative pi over 2 is going to equal, well, let's think about it. So get out your unit circle, and if we go to negative pi over 2, remember, if you're drawing an angle on the unit circle, if you have it in standard position, the vertex is at the origin, the initial side is the positive x-axis. If we go in the clockwise direction, we get a negative angle. If we go in the counterclockwise direction, we get a positive angle. Okay, so remember that. So if we're dealing with negative pi over 2, we're starting at the positive x-axis and we're going down negative 90 degrees. So at negative pi over 2, we have the ratio negative 1 over 0. So remember, tangent is sine over cosine. So on the unit circle, y over x. So we get negative 1 over 0, which is undefined. So that tells me we have a vertical asymptote at negative pi over 2. Okay? Now next we had negative pi over 3. So tangent of negative pi over 3, well, if we go to negative pi over 3, okay, we end up getting a ratio of negative root 3 over 2 divided by negative, or by positive 1/2. Okay, so again, get out your unit circle, you go negative pi over 3, that's going to be at 330 degrees or negative 30 degrees, or not pi over 3, negative 60 degrees, okay? So we have the y-coordinate is negative root 3 over 2, and then we're dividing that by the x-coordinate, which is 1/2. So when we do that, we get negative root 3 over 2 times 2 over 1, or negative root 3. So we have the ordered pair negative pi over 3, negative root 3, okay? And then next, let's see, we're going to do negative pi over 4. So negative pi over 4 is like negative 45 degrees, okay? And at negative 45 degrees, we have negative root 2 as our y-coordinate, and we're going to divide that by the x-coordinate, which is positive root 2 over 2. Well, we have a number divided by itself, so it's 1. It's just in this case, it's going to be negative 1. So we get the ordered pair, negative pi over 4, negative 1. Next, we're going to look at pi over 6, negative pi over 6. So that's negative 30 degrees, okay? So when we do that, we get that the y-coordinate is negative 1/2, and we're going to divide it by the x-coordinate, which is positive root 3 over 2. So again, make sure you've got your unit circle in front of you unless you have it memorized, okay? So this is negative 1/2 times 2 over root 3. So we end up with negative 1 over root 3. We would generally rationalize that, so we get negative root 3 over 3. So we have the ordered pair, negative pi over 6, and then negative root 3 over 3. Okay? Next, we have tangent of 0. So at 0, we have the ordered pair 1, 0. So we get 0 divided by 1 or 0. So we have the ordered pair 0, 0. Okay? So we go through the origin. And then at pi over 6, so that's positive 30 degrees. So at pi over 6, we have a y-coordinate of 1/2, an x-coordinate of root 3 over 2. So that's going to be 1/2 times root 3, whoops, times 2 over root 3, forgive me. So we get 1 over root 3. Again, we rationalize. Hopefully you're getting pretty good at rationalizing. So we get root 3 over root 3, which is root 3 over 3. So we have the ordered pair, pi over 6, root 3 over 3. Next, we have tangent of pi over 4, so that's positive 45 degrees. Here we get root 2 over 2 divided by root 2 over 2, so that's your y divided by your x, so that's just 1. So pi over 4, comma 1. Let me give myself a tiny bit more room. So we need to do next tangent of pi over 3, so 60 degrees. And at 60 degrees, we have that the y-coordinate is root 3 over 2, and we're going to divide that by 1/2. So that's root 3 over 2 times 2 over 1, or just root 3. So we get pi over 6, comma root 3. And then finally, it took us a minute, but we get tangent of positive pi over 2. Well, at pi over 2, we have the ordered pair 0, 1 on the unit circle. So that's going to be 1 divided by 0, which is undefined. And that tells me that I have another vertical asymptote. Okay, so what we're going to do is we're going to go back to the original worksheet and we're going to make note that we have vertical asymptotes at negative pi over 2 and positive pi over 2. So the ends of our period are always going to be vertical asymptotes. And then we're going to plot these other points in the middle. And just really quickly before we get going too far, if you have a calculator, root 3 is like 0.5 something. So we have root 3, which is, or it's 1.73. So this is going to be like negative 1.73. This is going to be like 1.73. And then root 3 over 3 is 0.57. So we'll say about 0.6. So this is going to be negative 0.6. This is going to be approximately positive 0.6. So just keep that in mind. We're going to have to kind of eyeball those when we go to graph them. Okay. So let's go back to the original worksheet. Sorry for the shifting. Again, my technology is at best, but we use it and we make the most of it. Okay. So here's our worksheet. So you've got your table filled in with those ordered pairs. Remember, if it says undefined, that means vertical asymptote. Okay. So here's our graph. Let me expand it just a smidge. So we're going to graph from negative pi over 2 to pi over 2. So this represents one period, because remember, a period is pi. So from negative pi over 2 to pi over 2, we have pi radians. Okay. Now we're going to go ahead and put in asymptotes, and let's do them in red so they like really stand out so we can see them. We know that at negative pi over 2 and pi over 2 tangents undefined. So that tells me I have vertical asymptotes here. So we generally represent asymptotes with dotted lines. So we have vertical asymptotes here. So that means our graph is going to approach these asymptotes and it's going to get closer and closer and closer, but it's never actually going to cross. Okay. Now the points that we have. So the first point in your table is at negative pi over 3. So at negative pi over 3, we had our y-coordinate was negative root 3, which is about 1.7, a little bit more or a little bit less than 1.7. So at pi over 3, we're going to go down to about here. Okay. Now at pi over 4 is directly in the middle of these two. Okay. At pi over 4, we had a value of negative 1. At pi over 6, we had negative root 3 over 3. So remember, that's about 0.6. So we're going to say it's about here. And then we had tangent of 0 is 0. So we cross through the origin. And then we have pi over 6, we had root 3 over 3. So root 3 over 3 positive is about zero point 0.6, so it's about there. And then at pi over 4, we have positive 1, and pi over 4 is exactly between pi over 6 and pi over 3. And then pi over 3, we had root 3, which is about 1.7, so we'll say it's about here. And then finally at pi over 2, we know it's undefined, so it's not gonna happen there. So the graph here is kind of it's kind of like a little wiggle, okay? So it sort of does this. And there you have it. Now, because this graph is periodic, it's going to keep doing this every pi radians, okay? So if we were to expand this graph, okay, let's say we expanded it this way, from pi over 2, we would have to go to 3 pi over 2, basically, okay? So we'd have to go over here to like 1.5 pi. We would have a graph that did like this. And then if we extended our graph in this direction, we would have another iteration that did like this. So this shape keeps going. It just keeps repeating every pi radians. Okay? So that is the graph of tangent. Here are some properties of tangent that are really worth understanding. We know the domain is everything except odd integer multiples of pi over 2. We know how to write that now. The range is all real numbers. And remember I told you, like when we were first learning about domain and range, it doesn't make sense until you see the graph. You can see now that as this graph does its little wiggle, it goes up forever and it goes down forever. So literally the range is everything, okay? We have that tangent is odd, so that means it's symmetric with respect to the origin. Okay, we know the period of tangent is pi, so every pi radians you repeat. The x-intercepts, if you look here, the x-intercepts, you can't really see them very well. We can only see this one right here. But the x-intercepts are going to occur at -2 pi, negative pi, 0, 2 pi, 3 pi. I forgot pi. There should be a pi in here. Throw in a little pi there. That's a typo that I forgot. So at integer multiples of pi, we have x-intercepts. The y-intercept is the origin. So this graph does go through the origin. Your vertical asymptotes are always going to occur at x-intercepts for cosine. Okay, so keep that in mind. Those are always going to be your vertical asymptotes. Okay, so in the next video, we'll look at cotangent.